Welcome back, everyone. So until now, we have discussed a binary search tree where each node has two and only less than two children. But now we are going to talk about trees in general. And what this means is that each node is not restricted to have some definite amount of children. So for example, we can have a node A which has 3 children. And then more generically, we can also have weights associated between information flow from A to B or A to C or A to D. Now, this means that this is a weighted, let's say, unidirectional graph or a tree. And then the information flow is weighted in between each nodes. And then we can also have what is known as a unidirectional or a bidirectional information flow, where you can say that information flows from node A to B with weight of 1.7, but it can also be the case where information flows from B to A with some different weight. Okay, so the trees, like any sort of a graph, can be represented in a tree, whether it's a bidirectional graph or a unidirectional graph. And not only so, maybe this is not a correct representation of saying unidirectional or bidirectional graph. You can also have a tree where let's say information is unidirectional between nodes A to B, but then between any nodes you can have information flow which is two directional. Okay, so we can have a case where in between different nodes we can have a two-dimensional flow, or maybe in between other nodes within the same tree, the information flows from parent to child only, or vice versa. Okay, so all of these representations form let's say a generic tree. So in this video we are going to just talk about representation. So the first thing that that you can think of is to not follow this sort of representation that I'm going to illustrate, but think about how can you represent trees, any type of tree where there is no restriction that if the tree is such and such, that then I'm going to use such and such representation. Okay, so the representation should be as abstract and as generic as possible. And so this is my representation, but you can also think of using adjacency list, or adjacency matrix, or whatever different sort of representations are there in literature. But this is just my own interpretation of this, let's say, generic graph or a tree. The first thing to notice is that I'm going to talk about these two keywords, breadth and depth. So depth increases, top down from, so the node A is at level D is equal to 0, B, C, D, N are at level 1, and E, F, G, H are at level 2. Okay, so the depth or height increases from top to down, and I mean, this can be like, this is not restricted. You can also say that this is the top root, the top root node is at D is equal to whatever maximum, and the depth increases from bottom up rather than top down. This is just a convention. And likewise, what I'm saying is that breadth increases from left to right, but it can be other way around. You can say that it's not the case that B is the first child of A. Maybe D is the first child of A and B is the last child of A. Whatever that order is in between, in between these three children of A is totally up to you. But just for the convention, I'm going to say that depth increases top down and breadth increases from left to right. And this leads to two different types of traversal. One is breadth first search, and the other one is depth first search, which we are going to study in the upcoming videos. But just to complete the representation of how am I going to represent this tree is by a class node. And when I say a class node, I mean that technically speaking, the name of the node and the associated weight that comes from information flow from parent to this child node. Okay. So this is how I'm going to represent a node with a string name and then a weight associated with information flow from parent to that specific node. Okay. And then, so this is how I will represent, I mean, an edge and a node in some sense. But then how am I going to represent this tree is via hash map. And so the first thing that you would see that I'm using a hash map, not a tree map, which means that there is no order in between individual key map entries that I'm going to list. So the hash map will contain a string as a key, and which will be the name of the node, and then all children of this node will be represented as value for that particular key. Okay. What this means is that, for example, I can define an array list of node A's children, and then I'm going to add these children, which in this case are B, C, and D. I'm going to add these three nodes as node A, as node A's children. And then I'm going to put, the string value of this node A as key and associated children of this node A as value. Okay. So the key value pairs will be the parent's name as string and all of the children represented as array list of nodes of associated to that parent name are values of this particular key. So here we define node A, like all of these three connections between node A and their corresponding children. Okay. And then likewise, we can do this for node B as well. If you see that this node B has only one child E associated with this 2.3 weight, and then likewise node C and then node D. So node C has a couple of children, node D has just one child. And then if you want to, let's say, I mean, for example, if you want to, here I'm saying that B is the child of A associated with this edge 1.7. But if you want to describe a two-dimensional flow between A to B, you can also say that, okay, make a child of B associated with some other weight. Okay, so the information flow is not only from A to B, but also from B to A. So in that case, you can simply define A as B's child. Okay, right now B is A's child. You can see so I'm here defining that B is the child of A, but then if you come over here, just define A as a child of B. So right now B has only one child, but if you just add this another line saying that node B dot add new node with value A and associated with some weight, then you can simply say that, okay, I'm going to define node A as a child of my node B with some other edge weight. Okay. And then, so basically this representation allows you to define any node as a child of any node in some sense. Okay. So this is how we are going to represent our trees in upcoming videos, where we are going to see different types of trees traversal. Okay.